Okay, so here's the new part of the lesson. So actually, in this part, there isn't anything new. We're just extending the things that we already know to include the complex numbers work that you've done with Mr. Fabregat's. So it's not that the roots of polynomial stuff is new, it's just that the complex numbers is an addition to that. So for this question, the roots of the quadratic ax squared plus bx plus c equals 0 are alpha equals minus 1 plus I over 2 and beta equals minus 1 minus I over 2. Please note that these are complex conjugates. So hopefully you've done, I'm sure you have, I reviewed this lesson, I'm sure you've covered that. So you should know that for an equation with real number coefficients, if it has complex roots, they will be conjugates of each other. And if you can't remember what a conjugate is, essentially the numbers are the same, so minus 1, 2 and 2, but the imaginary parts are the negative of each other. So one is positive and one is negative. And we would call, probably when you've done it with Mr. Fabregat's, you would call that alpha and that alpha conjugate, which would have a little star in the top corner, but we're calling it beta because our roots of polynomials are alpha and beta or alpha and beta and gamma, but they are complex conjugates. So what does it say? Find values for a, b and c. So we need to use the rules that we know for roots of polynomials. So we know that alpha plus beta equals minus b over a, and we know that alpha beta equals c over a. And if we know those things and we know those two, we can find integer values of a, b and c. So alpha plus beta will be minus 1 plus I over 2 plus minus 1 minus I over 2. So they've got a common denominator, so we can just add the numerators. Negative 1 add negative 1 is negative 2. I plus minus I is nothing. And we're left with negative 2 over 2, which is minus b over a. I'm not going to simplify that. I might simplify that in a minute, but I'm not going to simplify it for now. Here, alpha beta would be negative 1 plus I over 2 times negative 1 minus I over 2. So minus 1 times minus 1 is 1. Minus I squared minus I plus I, and we know that they always cancel out in conjugates anyway, over 4. So those two are gone. I squared is negative 1, so 1 minus negative 1 is 2. So that's 2 over 4, which is c over a. And I am going to cancel this one down. So I've got a half is c over a. So at this point, I can see that a is 2 on both of them. So I can say a is 2, which would make b also 2. And it would make c 1. So my equation, my quadratic, is 2x squared plus 2x plus 1 equals 0. So all the same work, just with the addition of complex numbers, which you already know how to manipulate. So that's good. Okay, next question. The roots of the cubic ax cubed plus bx squared plus cx plus d equals 0 are alpha, which is 1 minus 2i, and beta, which is 1 plus 2i, and gamma equals 2. Please look again. These, oh actually, I can put it on the screen, sorry. These are complex conjugates. The same real part, different signs of the imaginary part. So yeah, they always come in conjugate pairs. Find integer values for a, b, c, and d. So that's exactly the same. Except the rules for cubics, we need to remember that alpha plus beta plus gamma is minus b over a. Alpha beta plus beta gamma plus gamma alpha is c over a, and alpha beta gamma is minus d over a. Okay, so alpha plus beta plus gamma. So 1 minus 2i plus 1 plus 2i plus 2 is minus b over a. So that's alpha, beta and gamma. So I've got 1, 2, 4. Minus 2i and plus 2i cancel out, and that's minus b over a. So that gives me that one. This is going to be a bit messier. So alpha beta is 1 minus 2i times 1 plus 2i. Beta gamma is 1 plus 2i times 2. And gamma alpha is 2 times 1 minus 2i. And that's c over a. So here I've got 1. I'm going to put a line down here. Minus 4i squared minus 2i plus 2i. Here I've got 2 plus 4i. Here I've got 2 minus 4i. So what have I got? I squared is minus 1. Minus takes a plus, so I've got 1 plus 4 minus 2i plus 2i cancel out. 2, 4 again. And 4i and minus 4i cancel out. So I've got 9 is c over 8. If I squish this bit on here, can you still see that? Alpha, beta, gamma is 1 minus 2i, 1 plus 2i times 2 equals minus d over a. Alpha, beta I've already multiplied out here, and I know that it gave me 1 plus 4, so 5. So I know that that is 5 times 2 is 10, is minus d over a. In all of these, there's no denominator, so I can say that a is 1, which then makes b minus 4, negative 4, c is 9, and d is negative 10. So, well, it says find integer values for a, b, c, and d, which is what I've done, but my equation, if I put them back in, would be x cubed minus 4x squared plus 9x minus 10 equals 0. So those are my integer values, but that would be my equation. Okay, and lastly, so the cubic 2x cubed minus kx squared plus 30x minus 13 has roots alpha, beta and gamma. Write down the values of alpha beta plus beta gamma plus gamma alpha and alpha beta gamma, and express k in terms of alpha beta and gamma. So this is just an extension of what you've done before. We're going to be using the same results. Alpha plus beta plus gamma equals minus b over a, and so on. It's just that now we're moving into exam style questions. So we've got marks coming into it, and you know, as part of that, you suddenly have an unknown, so in this case, k appear in the question, but the method is exactly the same. So first of all, for this one here, we know that alpha beta plus beta gamma plus gamma alpha is c over a. Write down the values of, oh, okay, so a, b, c. So alpha beta plus beta gamma plus gamma alpha is a, b, c, 30 over 2, which is 15. Alpha beta gamma, we know that alpha beta gamma is minus d over a. So alpha beta gamma is a, b, c, d minus d, so 13 over 2. And express k in terms of alpha, beta and gamma. So if we look at k, it's the b term, so we're going to be using alpha plus beta plus gamma, which is minus b over a. So alpha plus beta plus gamma is minus b, so minus k, minus k. So k over a, which is 2. So can I squish it on? I'm really going to try and squish that on. No, I won't. I'll put it underneath. So if I times it by 2, 2 alpha plus beta plus gamma equals k. Okay, so that's the first part of the question done. Value of that one, the value of that one, and k expressed in terms of alpha, beta, and gamma. So 15. Right, given that alpha equals 2 minus 3i. Oh, this is nice. So, for part B, alpha equals 2 minus 3i. So you straight away know that because this is real number coefficients, if one root is 2 plus 3i, another root, I'm going to call it beta, must be the conjugate of that. So 2 plus 3i. So we know that already. And now we need to find the value of k. So we know that k is, this is all fitting on. So k is alpha plus beta plus gamma times 2. I know alpha, I know beta, so now I need to find gamma. I could find it from this equation, or I could find it from this equation. I'm going to use this one because it's got the least things going on in it. It's the easiest one to manipulate. So alpha is 2 minus 3i. Beta is 2 plus 3i, and gamma I do not know, but I know that when I times them together I get 13 over 2. If we multiply these out, we've got 4 minus 9i squared minus 6i plus 6i times gamma, which is 13 over 2. So those two cancel out. I squared is minus 1, so minus 9 times minus 1 is plus 9. Crikey, 9 out of 4, how's that so hard? 13. So 13 gamma equals 13 over 2, which means gamma is a half. And now I know gamma, I know alpha and beta and gamma, so I can use this one. And I know that 2 lots of alpha plus beta plus gamma is k. So plus 3i minus 3i, we've got 2, 4.5. So 2 lots of 4.5 is equal to k. So k is 9. And those are, that's a bit of an extension of what we've done before, but essentially that's the way that complex numbers creep into roots of polynomials. The work isn't different, it's just that now you're using a different type of number. This is what I would like you to work on now. So I've attached these exercises as PDF attachments to the email, and there's another sheet with the answers. So I would like you to work through those. I will send you worked answers later in the week, my worked answers, but for now, that's what I would like you to try.